In the previous video, we have shown how you can capture executed files using Tracee. This is a follow-up video where I'd like to discuss some of the implementation details behind this feature and maybe share some learnings and some of the issues that we faced and how did we solve them as a learning. So if you haven't watched the previous one, you can go and watch it now. I'm going to just demonstrate very quickly, just as a recap, what this feature is about. So on the bottom terminal, I'm running Tracee, telling it to trace execve at, telling it to capture executed files. And here I'm just going to run date. So Tracee has traced execve. We have all the information. If we take a look at the output directory, which by default is temp Tracee, yeah, we need to tell it what to do. We will see that date was actually captured for us. So this is a recap. Let's start thinking about how would you go about to implement this feature. So we already see a lot of information here that we can use, right? We see that execve was executed. We know that. We also know what's the path name that was used for execve. So it sounds like a good start. We can maybe take this path and copy it, right? Well, yes, this is a good start. Let's challenge this approach for a second. If we take a deeper look at the execve system call, we will see that it accepts the path name, and there is some documentation here for how the path name that the user provides, how it is treated. Actually, there's an entire article here about how the kernel resolves the path name that the user provides. There is quite a lot of business logic that happens here, and we wouldn't want to um, recreate this logic in our code in Tracee, right? We just want to get the end result. Another thing to consider is that execve has this sibling, this variant that accepts another argument, the drfd argument, and it affects how the path name is going to be resolved by the kernel. So, for example, if path name is absolute, drfd is ignored. But if drfd is provided and path name is relative, then it's relative to drfd, except if drfd is a special value, then path name is is relative to the current working directory, etc., etc. It's all documented here. I will not go into that right now because I want to avoid it. And because I want to avoid it, I am looking for another way to get to the actual binary that is going to be executed instead of relying on the user input, because the user input still has a long way to go until it reaches something, some artifact that is about to be executed by the kernel. So we know that the kernel has this struct, very handy struct, that's called Linux bin PRM, or binary program. And the kernel will populate this struct as it prepares to execute the program. So one of the fields here tells us about the actual path to the actual file that is about to be executed. This is an absolute path. This is after all of the magic that can happen in the kernel. So this is something usable for us. The question is, how do we gain access to this struct? This struct represents the file that the kernel will execute. How do we gain access to this? So the answer is not via the execve system call. Instead, we will trace something else. We will trace, for example, the security bprm check, yeah, event. Actually, technically, it's not a system call. For Tracee, it's the same thing, so we can trace it. This is part of the Linux security model subsystem, which I will not explain here. I'll just say it's a function in the kernel, and we can instrument it. And the argument to this function, is a pointer to this struct, to this BPRM struct. So if we have instrumented this, we have access to this struct, we can extract anything we want from it. This is great for us. So let's take a look. Now we are doing basically the same thing, except we are telling Tracee to also show us the security BPRM check event. And now we see that for the same user action that I did to run date, we get a couple of events. The same execve as before, but now also a security BPRM check event with some other information that we extract from it. So the path name here, right now in this example, it looks similar to the path name of execve, but the difference is very critical. This is the path name that the user provided. This is the input. And this is the path name that the kernel will load. This is like the output of this entire process. So in this case, the input and the output is the same, but in many other cases, it will not be the same. So one thing's for sure, we can use this. We can just go to this file and read it, copy it, do whatever we want with it. So this is one challenge that we have resolved. Okay, so let's keep going. We actually have another issue. I've shown in the previous video that Tracee can also capture executables from within containers. And this might be also a challenge. Let's see why. So I'm going to run Tracee here again, this time in container mode, which tells it to only capture newly created containers, to trace newly created containers. And I'm going to, let's start Tracee, and here I'm going to run a Docker container, Docker run. It's just an Alpine container, and I'm going to tell it to sleep for a while. And when I do that, we can see that Tracee has traced this entry point like we started sleep. First of all, let's pause here and see an example for the point that I was making earlier. Execve was given this path name, being sleep, but security BPRM check, or in other words, the BPRM struct, has this path name, being busybox. This is a good example for a case where the user provided input will not necessarily be what the kernel is going to load. And the reason for that is, in this case, the Alpine container, this is how it works. They just have a single binary that has the implementation for all of the common commands. So this is one point that I was going to make. But the other point is that, okay, we have this path here. If we try to save it from the same place that Tracee is running, which is here on the host, we shouldn't be able to. Yeah, because this file exists inside of the container and not on the host. So Tracee now needs to kind of reach into the container file system, into the container's point of view of the file system, and grab the file from there. How will we do that? So the solution that we found is to use the proc file system. If we take a good look at the proc file system, we see that for every process, let's pick just one process, 744, I don't know, there is this root subdirectory that, there it is, took me a while to locate, that is actually kind of like a gateway to see the file system root that this process is seeing. So in this case, we have this process that was started. We know its um, host process ID. This is the process ID on the inside of the container, inside of the process namespace, the PID namespace that was started for this container. It's PID1, but actually it's not really PID1. It's PID 9176 on the host. So we could do something like this. We can do proc 9176 root, and yeah, we need permission to do that. And this is the file system root inside of the container, or in other words, this is what this process thinks uh, is its file system root. If we compare that to the host root, you can see that this is a different file system. So this is a good way for us. Now we can prepend this into the path name that the security BPRM check event has given us. So if we do that now, bin busybox, yay, we have an access to the busybox binary from the host, even though the busybox binary is somewhere within a container. So this will work in this case, but now I want to show you another complication of that. So let's actually exec into this container. Docker exec, I don't remember, what was it? 1.6, okay. Docker exec 1.6, let's run a shell there. Okay, we see that the shell was started. And now I want to do the date. I want to execute date again. If we do this, we see again that date has started. It's actually busybox, but it doesn't matter for this for now. And if we go and look at the process ID, which is now 9310, we can exit this now, and we will use the same trick that we did before. 9310, no good. Why is that? Well, it's actually pretty simple because the date process has already exited, right? We launched it, it printed the date, it exited. We have its process ID, but it's no longer useful for us. So in case of a very short-living processes, it's going to be hard for us to try and capture them using their PID, their process ID, because they are short-lived. So the solution that we have found for that is to not use their PID, but instead to use the PID of another process within the same out namespace or the same container in this example. So we know that sleep has started as PID1. So in this case, what Tracee will do, it will use this process ID in order to get this process. All right, this is the solution that we have found for that. And the way that we are able to keep track of the process IDs is, we can also stop this now. Inside of Tracee, we have, just a sec. Okay, so this is the code of Tracee, the part of code that's responsible for this. We have this kind of cache where we cache inside of this PIDs in mountain S cache. We save here, this is just a map that maps from mount namespace to a list of PIDs, a list of process IDs. So we actually have this very simple logic here that says, okay, if it's PID1, if this is a PID namespace process, then for sure we want to save this process's host process ID, so we can use that in order to grab any executables that we will encounter along the way. And this is exactly what happens here. When Tracee saw this execution, it saw, okay, this is a PID1. I better save this 9176 under the mount namespace key in this map, so that later on when I see something else like this date execution, I will not try to use this process ID, I will try to use this process ID. This is the solution that we have for that. And what happens if processes share PID namespace, for example, or if a container shares the PID namespace with the host or something like that, which is not very uncommon, people do that. Well, in this case, we also maintain like a hot cache of some of the other processes. So in this example, we will cache this process ID, but we will also cache these process IDs. So if this fails, we will try the other ones, and we will try to refresh this cache as we go along. So we have this mechanism that we have built into Tracee to try to keep track of the processes within containers. It works pretty well, as you see here. Actually, you haven't seen, so let's show you that it actually works. So yeah, it's just BusyBox because everything here is Alpine. You see that the path name is always BusyBox, but we didn't get any error, which means that we were able to follow through what we wanted to do. And just Tracee was smart enough to not duplicate this file because it would be redundant. But we didn't get any errors, which means that this works. Tracee can capture executed files. It works from the host. It works from containers. It works if you share PID namespace or if you don't. It works if the process that you want to capture has exited quickly, and so on. I'm sure that there are many other edge cases that we didn't catch there. This is where we ask for your help. Try Tracee. Tell us what you think. I guess that I also wanted to show this video because I wanted to show that it's not that hard to contribute to Tracee. I mean, you don't need to be a kernel wizard or an eBPF expert. You actually don't need to understand a lot of stuff that goes on behind the scenes. In the end of the day, this feature, the capture exec feature, it's just Go code. I think it's pretty approachable. You see its implementation here. So, if the user wanted to capture exec, we get the path name, we do some, we prepare the output directory, the destination file, and so on. We try to look for the file under the proc file system, as we've seen. Copy by file path, it's what actually does the copying. Pretty trivial Go code, I think. So maybe this can encourage you to take a look not only at using Tracee, but also at contributing to Tracee. And we'll be thrilled to help you on board that. So if you have any questions, if you want us to help you find your way around the code base, please reach out. You can jump on our community calls that we have. You can engage in GitHub discussions that we have in our GitHub repo and so on. Yeah, so that was it. I hope you enjoyed it, and see you next time. Thank you.